Hi, good afternoon, everyone. Yeah, as introduced me already, I don't need to say too much about myself. Other than I work for Binnies, and I'm based in their Chester office. And yeah, the subject of my talk is about fish pass design and how to use Flood Modeler to aid that. Uh, and that's the main focus. And then there's a little bit on flood risk as well. So what am I going to talk about? I'm going to talk about the location where we've done this design work on these fish passes. I'll talk a bit about watercourse characteristics um, and the catchment characteristics, and then we'll look at each of the two sites, which is Pelena Culvert and Pelena Weir. I'll then cover a bit about the flood risk before drawing some conclusions and then questions at the end. I should say that both these sites were commissioned by NRW, so thank you to them for allowing me to use this to present. So where in the world are we? So we're in South Wales, sort of in the valleys. On the picture on the right, you can see it's not far away from Neath. The Afon Pelena runs in a generally south to southwest direction. It's actually called something slightly different at the upstream end, but my Welsh pronunciation isn't quite up to it, so we're just going to call it the Afon Pelena. It continues in that southwest direction and discharges to the sea at Porth Talbot. The catchment, so because I do some hydrology as well, I like to look at the characteristics of the catchment. So on the right hand side, you can see the catchment boundary taken to the Pelena Weir site, which is the downstream site. The Pelena Culvert site is further upstream. You can probably see a small red dot towards the upstream end. So these are quite small catchments. So to Pelena Culvert, it's only 3.5 kilometres squared. To Pelena Weir, just over 6 kilometres squared. Then looked at some of the catchment descriptors. So the DPS bar gives us an idea of the steepness of the catchment. So it's 85 meters per kilometer for Pelena Culvert, and it actually gets steeper as we go downstream to Pelena Weir, which might seem a little unusual, but if we look at the shape of the catchment area, we can see that it actually narrows as it goes downstream, and it becomes a really quite steep-sided valley. DPL bar is average drainage path length. As you expect, that slightly increases between the two sites as the catchment area increases. The average annual rainfall for this site, which is the SAR value, is nearly 2 meters. So to put that in context, I'm sat here in snowy Chester today, and the average annual rainfall for Chester is about 700 millimeters. And then the BFI host value, that gives us a bit of information about the permeability of the catchment. Typical values range from about 0.2 up to 0.9697. The higher the value, the more permeable the catchment, and the lower the value, the less permeable the catchment is. So in this case, those values indicate that this catchment is relatively impermeable. And what about the watercourse? So there's some photographs on the right which give a typical idea of what the watercourse looks like. So it's either the bed is either bedrock or it's made up of large cobbles and boulders. It's flowing through a forested area. It's quite fast moving, high energy, with lots of riffles. And so what about the flow conditions in the watercourse? So because we're looking at fish passage, we're actually looking at what you might call normal flows rather than flood flows. This is all about fish migrating upstream, and they migrate upstream in normal flow conditions. So how do we describe normal flow conditions? Well, we use something called exceedance flows. An exceedance flow is the flow which is equaled or exceeded for a given percentage of the flow record. So the way I like to think of this is, what does that mean for a typical year? So if you look at a Q95 exceedance flow, that means that that flow value is a flow that has exceeded 95% of the time over a year, which in a typical year would be 347 days. Whereas a Q10, that's a flow that's exceeded 10% of the time, so that's only exceeded 36.5 days of the year. On the right hand side, you can see I've got a table with some of those exceedance flows values in for the two sites. So you can see they're quite low, particularly at the Q95 and Q90. That they might almost be better described in litres per second rather than in QMEX. To put some context to how these compare to flood flows, I've put the QMed, or the 1 in 2 year flood flow, on the right hand side. So you can see that flood conditions are much higher flows even compared to the Q10. And what about the fish? Which fish are we trying to help? So we're trying to help fish migrate upstream. So these are some of the fish species that have been found present in the Afenpolena, not necessarily at the sites we're going to be looking at, but have been found in the Afenpolena. So starting at the top left, we've got the Atlantic salmon, and then next to that, we've got some brown trout. Then at the bottom, bottom left, we've got the European eel, and next to that are the slightly freaky looking lamprey. So I think that picture is from an aquarium, but they honestly really do look as weird as that. And there's also another species of fish called the bullhead, which I don't have a photograph of. So let's move on to the first of the sites. So this is the Polena culvert. So this is the upstream site. So what are the obstructions at this site? What are the obstructions impairing fish passage? So first of all, as the name might suggest, there is a culvert. It's quite a long culvert. It's 18 meters long. It's got just over 2 meter diameter. Within that culvert, they have installed some 0.2 meter high baffles, which are there to try and aid fish passage. But a lot of these have come loose or just been washed out by the flows and the sediment that is being moved downstream. At the downstream end of that culvert, if you look at the picture number 2, the bottom right, you can see that there's quite a steep ramp coming out of that culvert, flowing into a pool. So that's kind of high, very high energy. It makes it very difficult for the fish to actually get up to the culvert to enable them to have a go at then get to swim upstream through the culvert. And then if you look at the top picture, we have got quite a large blockstone weir, about 0.0 meters high, which is helping to form that pool downstream of the culvert. Now at this point, I should say that we agreed with NRW that it was going to be a case, and the design works going to be a case of best endeavours. We would follow what's called the fish pass manual, which is the guidance document for designing fish passes, as best as we could, but we weren't going to be able to keep all the fish happy all of the time. So how did we go about modelling it? So obviously, first thing we needed was to get some survey. So on the left-hand image shows you the water courses and the route that it's taking. So the Afenpolena is flowing westwards and then turns southwards at Polena Culvert, and then coming in from the north is a small tributary to the Afenpolena. So we got some cross-sectional data, and also we also got some much more detailed survey data around the culvert and downstream of it. And this was quite useful because it allowed us to have additional information. If we needed more information or additional cross sections, we could use that information to add to the model. So this is the model schematic, which in itself is not all that interesting. I think the points to highlight here are the long culvert. We modeled that using the circular conduit unit. There is a spill included in parallel to represent overtopping of the culvert, which really only applicable to flood flow conditions. The various weir structures modeled using spill units because they're obviously very irregular profile. We've slightly lowered the weir coefficient of discharge for those structures to represent those. So rather than a standard 1.7, we've lowered it to about 1.5. The other thing to add is that we had to put quite a few interpolate sections in just to aid the model to run. So we then ran the model. So how did we go about doing that? So we just ran it in steady state. We didn't need to run it in unsteady state. We're just running it for a series of flow conditions for a single flow value. We haven't got hydrograph, so we could run it, just run it in steady state. When we did that, this is the initial result that we got. So you can see that through the culvert and downstream of the culvert, the water surface profile looks quite sensible. But upstream of the culvert, we've got this slightly odd mound of water, which doesn't quite look right. So why is that happening? Well, that mound of water is where the small tributary is coming in. And the channel at this section is particularly non-uniform, and we're getting some very high velocities, which resulting in the Froude number exceeding 1, which means that we're getting supercritical flow. So how does Flood Modeler deal with supercritical flow? Well, generally it approximates the answer, and most of the time that gives a perfectly acceptable answer. But when things become particularly non-uniform and you get some very high velocities, then that answer becomes more approximate and you can get some spurious results. However, Flood Modeler does have a solution to this. If you're running a model in steady state, you can click a little box which gives you the transcritical solver, and this then uses the full equations to give you the results. And the result of that is you can see now upstream, that mound, which is shown by the red line, has disappeared. Sorry, that mound has disappeared, and now we've got a much more sensible water surface profile. So this slide, we're just looking quickly at the results of the baseline. So this is before we've done any work. So at the issues here are at the culvert outlet. So we're getting some very shallow depths of flow at the outlet of that culvert. So in the Q90, we're only getting 0.03 meters. And even in the Q10, that's only 0.16 meters. We're also getting quite a large head loss across that downstream weir of up to 1 meter in the Q10, which makes it quite difficult for all these fish species to pass. However, as I said, we couldn't solve all the problems, and so it was agreed with NRW that existing weir would remain as is, and that the focus would be very much on allowing or improving the chances of fish passing up through the culvert. So my colleagues who completely understand the fish pass manual came up with a design which is shown on the right hand side. So the idea was to basically create a couple of pools to get rid of that ramp downstream of the culvert, and so this is basically formed by creating a couple of new weirs, each with a small notch in, about 600 mil wide and 250 mil high. So the idea is the fish come swimming upstream, they hopefully get over that first existing weir, and then if they need to, they can have a rest in that first pool before then making it over that first notched weir into another pool. Again, that allows them to have a rest if they need it before they then try to traverse upstream along the culvert. So these are the results of that. So we can see that now the minimum depth of flow at the culvert outlet is now increased to 0.26 meters in the Q90, and then across each of the weirs that we've added to as part of the fish pass design, that minimum depth of flow is now 0.15 meters in the Q90. So that is probably the minimum depth of flow you'd want for fish passage, but that increases quite a lot to 0.26 meters in the Q50, which is much more acceptable. We do still have that head loss across that existing weir because we've not changed anything there. So often when we do this kind of work, sometimes it just goes and then sits on a shelf and nothing happens to it. But in this case, it went all the way through outline design, detailed design, all the relevant permits were achieved, and they were able to construct it. So these are a couple of photographs. So on the left-hand side, got the culvert, which shows they've reinstalled the baffles, so you can get a much better idea of what those baffles look like. And then on the right-hand side, we're looking upstream towards that culvert, and you can see the pools and the notched weirs, and you can see it's quite natural, sits into the surroundings quite well, and it, I'm not a fish. Sorry, I'm not a fish, but it looks like something that a fish might be able to swim up relatively easily, hopefully. So definitely an improvement on what was there before. So if we move on to the second site, so this site again is similar, very similar. We've got a series of obstructions at this site. So starting upstream, we've got a boxstone weir, 0.6 meters high. That's shown in the top right. Moving downstream, we've then got a masonry weir, which is the bottom left photograph. And then we've got a bridge, which doesn't in itself cause an obstruction, but it's got a concrete apron. And then downstream of that concrete apron, it's scoured away the natural bed. And so we've got quite a large drop there, about 1.2 meters. And then downstream of that, there's a further weir that, similar to the first site, potentially causes a bit of an obstruction to fish, but that was basically not included in our scope to look at. So we were very much looking at those first three obstructions. This is very similar. Again, got lots of survey sections to build the model with. Again, that really detailed survey. That really detailed survey to help if we needed additional information in the model. This again, schematic, not an awful lot, not all that interesting. Again, those weirs have been represented as spill units with the coefficient of discharge slightly reduced. And we've included the bridge unit with a spill unit in parallel to represent any overtopping or bypassing when we look at the flood risk aspect of it. So moving on, again, looking at the baseline results. So we can see that the issue here again is a shallow depth of flow across each of the weirs. So we're looking at sort of 160 mil across the first weir in the Q95. That's only 110 mil across the weir 2, and then 160 mil across the third weir. We've also got quite a large head loss, so more than half a meter across weir 2, and then over a meter across weir 3, which is that big weir where the bed has been scoured. So again, the guys came up with a couple of options to look at. So these two options have one similarity, is basically they've got the same solution upstream of the existing bridge, which was basically to remove the weir immediately upstream of the bridge and to regrade the bed, and then to put a notch in that most upstream weir. Then there's two different solutions here downstream of the bridge. The first option is very similar to the Palermo culvert option, which was to create a series of notched weirs and pools. In this case, it'd be 6 pools. The second option was basically to regrade the bed and create a couple of rock ramps with a pool in between. So we tested both of those. We gave the results back to my colleagues who had a look at that, and they came up with a third option, which is most closely related to option 1. So it was basically the same, but they reduced the number of pools to 4 downstream of the bridge rather than having 6. I should also say that upstream of the bridge, the idea was then also to put in a low flow channel, which would be sinuous. So this would increase the path length between weir 1 and the bridge, and therefore reduce the gradient and hopefully increase the depth of flow along that reach. So this is a summary of the results. So if we look at the depth of flow, we can see that downstream of the bridge, we've got a minimum depth of flow of 0.17 0.7 meters in the Q95, and then that increases to 0.29 meters in the Q50. So reasonable results for fish passage. The head losses are all less than half a meter, which again, good for fish passage. Probably the one issue that did still remain is that in that regraded channel upstream of the bridge in the Q95, we've only got 0.1 meters depth of flow, which is below really the minimum requirements. But by the time we get to Q50, that has increased to 0.2 meters, which is much more fish friendly. And so got some photographs again of the construction of the results once it was constructed. So this is looking upstream from the bridge. This is the upstream weir which they've put the notch in. And then on the right hand side, again, that's looking upstream from the bridge along the regraded channel. It's not very easy to see the sinuous channel. I think you can sort of make it out, but you can clearly see how it's been regraded. And then this is looking upstream towards the bridge. So you can see that big scour hold has been removed, that they've put in some large blockstone weirs. Particularly on the right hand side, you can see quite nicely that sequence of weirs and pools to help the fish pass upstream. So what about flood risk? So we did look at flood risk as well. So in order to build these fish passes, they needed a flood risk activity permit, or a FRAP. So we ran the model for the 100-year, the 1,000-year, and 100-year plus climate change events. We stayed in steady state. So because it's in quite a confined channel, there's not really much of a floodplain. You're not going to store any water in the floodplain, so there's not going to be an attenuation of flows. So running the model in steady state was fine. So we just ran it for the peak flow for each of those events. At Plena Culvert, there's no change to peak water levels upstream of the culvert or downstream of that existing blockstone weir. At Plena Weir, we actually got a slight reduction of water levels upstream of the most upstream weir. That's because of the notch that's been put into that weir. And then downstream of the site, there was no change. So all those so it's basically no detrimental impact from installing those fish passes. So to draw a few conclusions, the first thing is to say, well, flood model is not just for floods. We can use it for other things, such as designing fish passes or aiding the design of fish passes. We can use it for river restoration projects. We can use it for low and normal flows. We don't have to just use it for flood flows. It's also worth considering, if we've got a 1D only model, what's the best method of simulation to meet your needs? Do you need to run it in unsteady state? Is steady state an acceptable method? If we haven't got any storage to talk of, then running the model in steady state is quite acceptable. And then the advantage of being able to run something in steady state is that we can use that transcritical solver. And when we're running it in steady state, it's quite likely to be in a steep catchment with a narrow valley where the floodplain is likely to be minimal. Oh, and then this last bit, I'm just going to play a little video, which is the Plena Culvert site. Maybe, or maybe not. Oh, there we go. So this is just swinging around to look upstream. And that brings the end to the presentation.